Okay, good morning everyone. Today we will talk about fission, and fusion. We will describe the process of nuclear fission to describe the process of nuclear fusion. We do some calculations related with fusion and fission. Um, a little bit about how a nuclear reactor works. Okay. Now, when does spontaneous fission occurs? We talked about it, also last year we talked about it, yeah. Large nuclei, bigger than 92 protons, they are unstable and they usually will decay, yeah. It's very rarely that a large number nucleus will split up spontaneously into smaller nuclei. And the splitting of this nucleus is called fission. So splitting of an atom is called fission. Yeah. When it happens by itself, we call it spontaneous fission. Now let's look at our liquid drop model. Let's say we have a big drop of oil. Yeah, you can imagine the bigger the oil drop becomes, yeah, it will kind of fall apart, yeah. Now when we are looking in the nucleus, we see that the nuclei are not tidy and neatly arranged in rows, neutrons or protons, yeah. We also know that there is a strong nuclear force that acts between them to keep the nucleus stable, to keep it stable also from the electrostatic forces. Now the nucleons, they are not always linked together, but it's like they are jiggling, swapping around, yeah. But there are enough nucleons together, yeah, to stop the repulsive electromagnetic force that could actually tear the nucleus apart. And we're talking about the protons in this case. Now, when does spontaneous fission occurs? As I said, if that drop is too big, yeah, the strong force is too weak to hold the drop together and it can split the nucleus by itself, yeah. We also discussed already the limits of the number of nucleons that nucleus can contain. There's a maximum. Actually, the last decennia they have made some new elements with a very high atomic mass number, but they only could exist for milli or microseconds. Yeah, so very big atoms, they will spontaneous split, so they will undergo fission. Let's look again at our drop model. Yeah. As I said, they are like swapping and moving around all the nucleons, and we can actually induce a fission by bombarding the nucleus with a neutron. Yeah. And if that neutron hits in a weak spot, yeah, as you can see in the first picture, yeah, there's a weak spot. That means in that weak spot there are pretty much a lot of repulsive forces by the protons, and if that neutron hits that spot, excuse me, the drop can then split into two new nuclei. Now, just one note. Nuclear fission has nothing to do with radioactive decay, yeah? However, the parent nucleus will decay by normal radioactive process, and the daughter nuclei that occur may be radioactive, but they are two completely different things. In order to start an induced fission, Well, we know already larger nuclei are more unstable. That means it is more likely that we can induce a fission easier with larger nucleus. We can induce a fission in uranium-235, but another common isotope of the uranium-238 does not split so easy. Yeah, so we need to have the uranium-235. Yeah. Now, to induce the fission or the splitting process, it is done by a neutron that is bombarded on the nucleus. But this neutron needs to have the right kinetic energy. Yeah. So what we mean by thermal neutron is like the kinetic energy of the neutron. Yeah. And it needs to be close to the kinetic energies of the moderated molecules. Now, if the neutron doesn't have enough kinetic energy, that means it will bounce off. If the neutron has too much kinetic energy, then the neutron goes right away through the nucleus. So the neutron needs to have the right energy in order to break up or to split up the nucleus. Yeah. And it is like the same energy inside the nucleus and to give that resonance. Yeah. Okay. So it is always a common mistake that people think that in order to induce fission you need a very high speed. Neutron, this is not the case. It's actually relatively a slow speed neutron that needs to hit the nucleus. Okay, let's have a little bit of closer look to the nuclear fission. On the left side we see the neutron hits a very heavy nucleus and splits up in a heavy nucleus and a light nucleus. Meanwhile, it also gives off 3 neutrons. These 3 neutrons again can split up a heavy nucleus. Yeah. And this process keeps on continuing, new nuclei, and they keep on producing more neutrons. If this process is not controlled, we get the so-called chain reactions. Yeah. And they are able to split a lot of heavy nuclei. Yeah. We're not going to discuss how we can control this process, but in a nuclear reactor this process is controlled. Yeah, and to minimize the chance of getting a nuclear reaction. Okay, let's look at some fission products. We have, for example, the nucleus of uranium-235-92. It's hit by a slow moving neutron and releases xenon-134 54 plus strontium-138 plus 2 neutrons, or it could be split into krypton and barium. So there will always be a surplus of new neutrons that can split up again new nuclei. Now, how do we calculate the energy of this process? And we are looking at the top example, and the top example is the uranium-235 into xenon and strontium. Now, well, we have to look at the mass deficit of the process. So we're going to look what are the masses of the uranium-235, the neutron, we add them up. Then we add up the masses of the xenon, the strontium, and the neutrons, which gives us also a number, and then find the fission mass. That means the mass after minus before, and then we use Newton's equation to calculate the amount of energy that is released. Now a question for you. So pause the video and try to figure out the nuclear energy that is produced in the nuclear fission in joules and in electron volt. And if you may, you can also calculate it in mega electron volt. Let's look at the process. Uranium and a neutron splits into a barium and krypton and 3 neutron and an amount of energy. We add up the masses before minus the mass after, that is the mass defect. Can do it the other way around, doesn't matter, but we need to calculate the change in the mass. Okay, this will give us 2.988 times 10 to the negative 28 kilograms. We use E is mc square. We calculate the amount of energy, and in this case we get then 2.69 times 10 to the negative 11 joules, which is 1.68 times 10 to the power of 8 electron volts. So that is 168 mega electron volts. As stated, in order to calculate the energy, we need to calculate the mass effect. If there is an uncontrolled chain reaction, and this is given out in a violent explosion, and that is many times more powerful than just the explosion of TNT, and well, we know what are the consequences, what they did in Hiroshima. Yeah, the mass that actually is converted into energy is about 20 grams. Some disadvantages of producing energy from in a nuclear reactor. We have radioactive waste. We get daughter fragments after the process, and they have too many neutrons, and they are therefore highly unstable, and they decay by radioactivity, yeah, releasing all alpha, beta, and especially gamma rays, yeah. Another disadvantage is after an atomic bomb has dropped, there's a lot of dangerous fallout. Okay. Some uses of radioactive waste can be used for tracers, but we have to be careful. They need to be disposed carefully. We're not going too deep into this. Okay. Okay, let's talk about the sun. Who knows what kind of process is taking place in the sun to release energy? That is indeed fusion. Fusion is like coming together. So in fusion, the light nuclei join together, increases the binding energy per nucleon. Yeah, for example, 2 protons together make a hydrogen 2-1, give off some beta decay and a neutrino and an amount of energy. This process can continue, and the 2-1H can fuse together with a proton and make 3 helium plus gamma ray. Yeah, and even that can produce continue. It's like a continuous process, but these are the main reactions that are taking place in the sun to release energy. Yeah, but we know there are more common elements that are actually formed in the fusion process. Okay. This will result in a lot of energy. Yeah, it's about 25 mega electronvolt for helium nucleus, so that is about 6 mega electronvolt. So you would be thinking, why? Well, there is a very low radiation compared, or nihil radiation compared with nuclear fission. There are no radioactive waste products. Yeah. The problem is that in order to start this process and to let these protons and neutrons, to say so, to let them come together, you have to overcome the electrostatic forces and the highly strong nuclear forces. This is a process that actually needs to be controlled in a very strong magnetic field, and you need a lot of energy to start up the process, and that is one of the main problems. At this moment they can do nuclear fusion, but the balance of the energy is still negative. They still have to put more energy into the process than the process releases. Now let's look at our next question. We have the fusion of 2 1 hydrogen and 3 1 hydrogen. We get 4 2 helium and a neutron and energy. The mass of the deuterium is given, tritium nucleus is given, helium nucleus is given. If you don't know what is deuterium, that is hydrogen 2 1 and tritium is hydrogen 3 1. The mass of the helium nucleus is given and the mass of the neutron. So, how do we calculate the energy and the electron volt release in this reaction above? Again, we will look at the mass deficit. Okay? So try to find out what would be the energy. Alright, let's look at the process. On the left hand side, we calculate the mass. On the right hand side, we calculate the mass, then we calculate the mass deficit, which is then about 1.6635 times 10 to the negative 27 kilograms, using Einstein's equation, and then we get an energy 1.5 times 10 to the negative 11, and we can transform it, convert it into mega electron volts. As said before, what are some difficulties of diffusion? It means we need, I would say it in this way, it's not like that simple, just sticking neutrons and electrons and protons together. Yeah, you need a lot of electrostatic repulsion to overcome, and you need to be very close together so that that attractive force of the strong force holds them together. Yeah, and we are talking about a level of femtometers. Yeah, this means that in order to reach that, we need to heat up a gas at about an 8 times 10 to the 9 Kelvin, millions of degrees. At that time, well, when you heat up a gas at that temperature, it exists as an ionized gas, and it needs to be confined in a very small place, which is done by a very powerful magnetic fields. Yeah, the fusion has occurred, but it takes more energy in general than the energy that is released. So there's still a lot of technical issues to overcome to make this process happen. There are countries that are doing already research for several years, and I think even in France they have built a new reactor in order to see if they can improve the process. Okay, I will send a video about the Tomahawk reactor, and then you will understand a little bit why it is so difficult. Okay, now some common mistakes. If we compare the speed of many particles in nuclear and particle physics, it is pretty sluggish. Yeah? Remember, we tend to say that the nucleus are smashed by pieces by neutrons, but it's actually more tickling the neutrons. So we are talking about neutrons with a very relatively slow velocity. And don't forget to confuse fission is splitting up, fusion is coming together. Okay, in summary, for this unit we talked about it again: the atomic mass unit, mass effect, binding energy, fission and fusion. Okay,